Hello again, my name is William Pye, and in this video we will be talking about arguments and the rules of inference. So over the last couple videos we've been talking about the connectives and some of their properties. What we want to do here is start using the connectives to start making arguments and also to start building what are known as the rules of inference so that we can build larger arguments as well as more complicated proofs. After introducing the connectives and developing some of their properties, one can now turn to argumentation and reasoning. To this end, the notion of an argument is established. However, not all arguments are sensible. As such, the concepts of validity and soundness are also presented so that one can parse good reasoning from poor. Then, some simple arguments are demonstrated. Called the rules of inference, these common arguments will be used to construct more elaborate arguments and proofs. So what is an argument? Is it a shouting match between two parties trying to get larger volume than one another? No. In logic, an argument is meant to convince one of an implication, basically to deduce a fact from other given facts. Explicitly, an argument is defined in the following way. So, an argument is a series of sentences, basically a paragraph. The conclusion of an argument is its final sentence. A premise of an argument is any sentence other than that conclusion. So, with these definitions in mind, let's look at a sample argument. So, in this argument, the first sentence will be this: the traffic light is red. So, this is our first sentence, our first premise. The second sentence is, if the traffic light is red, then I will stop at the white line. So this is our second sentence, our second premise. The third and final sentence, our conclusion, is going to be, therefore, I will stop at the white line. Very often the conclusion is set apart by some adverb like therefore, hence, or thus. Very often the conclusion is very easily noted by one of these adverbs. Please note that the definition of an argument is very general. In particular, here's an example of something that can be classed as an argument given the definition we already have. Roses are red, violets are blue, thus cats are dogs. If this sounds like nonsense, it's only because it is. So, how do you tell between a good argument and a bad argument? Well, that's actually going to be one of our goals. In logic, the goal will be to provide valid and sound reasoning rather than nonsense like this. So what do you mean by valid and sound? Well, let's start with valid. An argument is valid if the conclusion cannot be false when the premises are true. Otherwise, the argument is invalid. So, an argument would be invalid if the premises are true and the conclusion is false. If that sounds familiar, it's because it sounds like the implication. The implication is false if the hypothesis is true and the conclusion is false. So, in which case, an argument is invalid if a certain implication is going to be false. And it would be valid if the implication was true. Thus, one can equivalently say that an argument is valid if the conjunction of its premises implies the conclusion. Consequently, the argument I have above here is going to be invalid. The reason being is because even if I have a red rose and a blue violet, that does not guarantee that cats are dogs. On the other hand, an argument being valid does not guarantee that its premises are true. That is, an argument might be valid, but not apply to a given situation. Recall again the argument that I gave a little while ago. That is, the traffic light is red. If the traffic light is red, then I will stop at the white line. Therefore, I will stop at the white line. Later, we're actually going to show that this argument is valid, an instance of what's called a modus ponens, one of the rules of inference. However, what if the traffic light is green? Well, if the traffic light is green, it's certainly not going to be red. So, in this case, one of the premises is going to be false. And that false, when conjunction with other premises, no matter what they are, will collapse to being false because of how the conjunction works. Thus, false implies true or false will be true because of how the implication works. In particular, the implication will still be true if I do not stop at the white line. So, this type of situation motivates the next term, what's called a sound argument. An argument is sound if it is valid and its premises are true. So it's valid, that is, the logic makes sense, but also the premises are actually true in reality, so the argument actually applies to reality. Now, to this video, we're actually going to focus mainly on valid arguments, but something to keep in mind is whether or not the argument is actually sound. Does it actually apply to reality or not? With the notions of valid and sound arguments, some simple arguments will be given and shown to be valid. Many of these argument forms date back to the great philosophers of antiquity, such as Plato or Aristotle. Consequently, the arguments are often named in Greek or Latin, such as we have the law of hypothetical syllogism, We have the law of adjunction, we have the law of simplification, the law of addition, the law of detachment, which has the Latin name modus ponendo ponens. We also have modus tolendo tolens and modus tolendo ponens. Below, each of these arguments will be shown to be valid, and we'll also give an example of each so that you can see how each of these is actually being used. Let's start with the law of hypothetical syllogism. So, a hypothetical syllogism has two premises that lead to a conclusion. The first premise is P implies Q, the second premise is Q implies R, and the conclusion is P implies R. So the three dots here are serving the same role as therefore or thus, basically showing you where the conclusion is. So we have two premises, and the conclusion is set off with these three dots. So I want to show that this is a valid argument. So to do that, I would take the two premises, conjunction them, and show that the implication to the conclusion is actually a tautology. But we've actually already done that. That's the implication. That's the transitivity of the implication. We already showed that with the truth table not long ago. That is that if you take P implies Q, conjunction Q implies R, this implies P implies R. We showed that that's always true. Thus, this argument form is actually always true. This is a valid argument. So, let's give an example of such an argument. So let's start with the first premise. The first premise here will be, if a storm begins this afternoon, then I will stay home. The P here is, a storm begins this afternoon. The Q here is, I will stay home. The second premise, if I stay home, then I will read a book. So I have my Q, I will stay home. The R here is, I will read a book. Okay? So the conclusion here is, therefore, P implies R. P being, a storm begins this afternoon, and the R, then I will read a book. So, therefore, if a storm begins this afternoon, then I will read a book. So this is actually a valid hypothetical syllogism. Next, let's look at the law of adjunction. The law of adjunction, much like the hypothetical syllogism, has two premises and a conclusion. The first premise is P, the second premise is Q, and the conclusion is a little silly. It's P conjunction Q. So we have P, Q, therefore P conjunction Q. Now, I want to show that this is a valid argument. To do so, again, I would conjunction the two premises and show the implication to the conclusion. That is, I would look at P conjunction Q implies P conjunction Q. But this is a tautology because the reflexivity of the implication. Every statement implies itself. Therefore, this has already been shown by a truth table previously when we showed the reflexivity of the implication. This is indeed a valid argument. It's not a very elaborate argument, but it is an argument nevertheless. So let's show an example of one real quick. So my first premise is the following. Roses are red. My second premise is roses are flowers. So there's my P, there's my Q. My conclusion here will be P conjunction Q, so both of these at the same time. That is, therefore, roses are red and flowers, both P and Q. So this is a valid adjunction. Next, let's consider the law of simplification. The law of simplification has a single premise that leads to a single conclusion. The premise is P conjunction with Q. The conclusion is that P must be true. So basically this means that I can rip off the Q and throw it away and regard P alone as being true. So to prove this, to show that this is a valid argument, then what I need to do is take P conjunction with Q and show that that implies P. Unfortunately, that implication is not one that we've actually shown already with a truth table or some other means. However, we have enough machinery that we could do it. If you wanted to, you could do this with a truth table, but I have all these properties we've already established, so this actually resolves into becoming a calculation. So let's look at P conjunction with Q implies P. So remember, the implication can be rewritten as negation of the hypothesis, disjunction the conclusion, giving me the statement here. By De Morgan's laws, the negation can be distributed at the cost of changing conjunction to disjunction. From here, I'm going to actually commute the negation of P and negation of Q to get the P's close together. Now the disjunction is associative, so I can regroup this so that the P's are together, giving me negation P, disjunction with P. By the law of excluded middle, this statement becomes purely true, and true is an absorbing element for the disjunction, so no matter what negation Q is, it absorbs into the true, giving me a true statement here. By the transitivity of the equivalence, this statement is equivalent to this statement, this statement, this statement, this statement, all the way down to the truth. Therefore, this statement is a tautology, and we now have that the law of simplification is indeed a valid argument. Now let's give an example of some simplifications. So in this example, here's my premise. Roses are red and flowers. In this case, my P is roses are red, my Q is roses are flowers. So to simplify this, I essentially remove the second of those two conjuncts, which will give me, therefore, roses are red. So essentially, I can ignore the fact that they're flowers and just say that the roses are red. So this is a simplification. For a second example, let's consider this simplification. My premise is going to be that Socrates was a Greek and a man. So the P in this case is Socrates was a Greek. The Q in this case is Socrates was a man. So the simplification is essentially ignore one of the two conjuncts. In this case, therefore, Socrates was a Greek. So here's another simplification argument. Now let's consider the law of addition. Much like the law of simplification, there is a single premise that leads to the conclusion. In this case, the premise happens to be P. The conclusion will be P disjunction with Q. As the name implies, what's happening here is you're adding in a second statement with a disjunction free of charge. Like with the simplification, this can be shown with a truth table. However, we have enough machinery we can actually do this by just doing a calculation with the previously established identities. So let's consider P implies P disjunction with Q. As before, the implication can be rewritten as the negation of the hypothesis, disjunction with the conclusion. So since the disjunction is going to be associative, we can regroup this, getting the P's together like so. So you have negation P, disjunction with P. However, this is the law of the excluded middle, which is always true, giving me a true statement, disjunction with Q, which will absorb the Q, giving me the tautology that I wish. Thus, this argument is indeed a valid argument. Now, to give an example of this, let's take the following premise. The premise will be cats are mammals, so this is going to be my P. I can disjunction with whatever Q statement I wish, as long as it is, again, with the disjunction. So I will disjunction with the statement Q, which is going to be cats are reptiles. Therefore, the conclusion here will be, therefore, cats are mammals or reptiles, giving me a valid addition. Now let's consider the law of detachment, what's known in Latin as modus ponens, or simply modus ponens. There are two premises that lead to the conclusion. The first premise is P. The second premise is P implies Q, and the conclusion is Q must be true. The idea is P is true, P triggers Q, therefore Q must be true. So, one can use a truth table to show that this is a valid argument, but I'm going to use the previously established identities to do a calculation. Let's look at the conjunction of the two premises imply the conclusion here. So, there are two implications, and what I'm going to do, much like the previous two examples I've given, what I'm going to do is rewrite the implication as negation of hypothesis, disjunction with conclusion. So, I'll start with the outer implication here. I'll rewrite that as negation of hypothesis, disjunction, conclusion. Now I'll do the same thing for the inner implication here, so negation of P, disjunction with Q, right here. Now, I have a conjunction sitting on top of a disjunction. By the distributive law, I can rewrite that as P conjunction with negation P, disjunction P conjunction with Q. Now, P conjunction with negation P is the law of non-contradiction, which is always false, which will give me a false statement here. Now, false is the identity element for disjunction, so it melts away, leaving me with just P conjunction with Q. Using De Morgan's laws, I can distribute the negation at the cost of changing conjunction to disjunction, give me this. Now, disjunction is associative, so I can regroup this with the Q's together to give me this. But this is the law of excluded middle. So the negation of Q, disjunction with Q, will give me a true statement, which will absorb the negation of P, giving me the tautology I want. Therefore, indeed, the law of detachment is a valid argument. Now let's give a couple examples of a modus ponens argument. First, let's actually do that traffic light example that I gave earlier and show that it is indeed a valid argument. The first premise was, the traffic light is red. This is my P statement, my triggering statement. The second premise was, if the traffic light is red, then I will stop at the white line. So if P, the traffic light is red, then Q, I will stop at the white line. So I have P, P implies Q, by modus ponens, therefore Q must be true. Therefore the conclusion statement here must be true. Therefore I will stop at the white line. So indeed this is a valid modus ponens argument. Now let's do a second example of a slightly different flavor. So here's a second modus ponens argument. The first premise is the following. The button is pressed. There's a button, I push it, so the button is pressed. So this is my P statement, my triggering statement. The second premise, if the button is pressed, then the light will illuminate. So if P, the button is pressed, then Q, the light will illuminate. So I have P, P implies Q. Therefore, by modus ponens, Q must be true. Therefore, the conclusion must be true. Therefore, the light will illuminate. This too is another example of a modus ponens argument. Now let's consider another argument that's very similar to the modus ponens, what's called modus tollendo tollens, or simply modus tollens. The premises here are very similar, but with some major differences. Specifically, we're going to start having negations show up. Specifically, the first premise is negation of Q. Now, we still have the premise P implies Q, but the conclusion is now negation of P. So, what's going on here? Well, we have P implies Q, P is the cause, Q is the effect. Well, the effect didn't happen. Therefore, the cause couldn't have been present either. Otherwise, the cause would have made the effect happen. This is basically working backwards in a sense. You know that the effect didn't happen, so we can conclude that the cause couldn't have happened either. Now, as before, one could use a truth table to show that this is a valid argument, but I'm going to use the previously established identities to do a calculation instead. So let's take the conjunction of the two premises, implies the conclusion, and see where this goes. What I'm going to do is rewrite the implications as negation of hypothesis, disjunction with conclusion, for the outer statement as well as the inner statement, giving me the statement below. So, this is very similar to what happened with modus ponens. However, notice that all the negations are running around. So that's actually something we're going to have to sort out as we go along. Now, let's apply the distributive law. So conjunction on disjunction will distribute, giving me negation of Q, conjunction with negation of P, disjunction, negation of Q, conjunction Q. Now, negation of Q, conjunction with Q, that is going to give me a false statement. Again, that is the law of the non-contradiction. So we have a false statement here. Now, false is the identity element for disjunction, so that melts away, giving me this. Applying De Morgan's laws, I can distribute the negation at the cost of changing conjunction to disjunction, but now you notice I now have some double negatives showing up. And by the Litotes law, those double negatives will go away, and that will give me P and Q respectively, giving me the statement here. Now, the disjunction is associative, so I can regroup this, putting the P's together. So I have P disjunction with negation of P, but that is the law of excluded middle, which is going to give me a true statement, and truth will absorb the Q no matter what its value, giving me a true statement at the end. Consequently, this is indeed a tautology, and therefore a valid argument. Now let's consider some examples of making modus tollens arguments. What I'm going to do is I'm going to take the modus ponens arguments I had before, tweak them slightly, and get modus tollens arguments instead. So let's start with the traffic light example that I gave before. Here I'm going to have the first premise be the following. I will not stop at the white line, so this is my negation of Q. My second premise is actually the traffic light example. So if the traffic light is red, then I will stop at the white line. So this is my P implies Q. So P in this case is the traffic light is red, then Q, I will stop at the white line. So I have P implies Q and negation of Q. So by modus tollens, I should get negation of P. So that is, therefore, the traffic light is not red. So this would be a valid modus tollens argument. Similarly, we can do the same thing with the push button and the light illuminating one as well. So here's a second modus tollens argument. My first premise is the light will not illuminate. Okay, so light will not illuminate. This is my negation of Q. My second premise is the implication. So if the button is pressed, then the light will illuminate. So this is P, the button is pressed, implies Q, the light will illuminate. So I have negation of Q, P implies Q, so by modus tollens, I should get negation of P. That is, therefore, the button is not pressed. So here's a second modus tollens argument. Now let's consider one more rule of inference. We have modus tollendo ponens. As its name implies, it's kind of a mix of the previous two laws of detachment. The premises go as follows. The first premise is negation of P, very much like modus tollens. The second premise, however, is P disjunction with Q. Now, this is going to serve the role of the implication, P implies Q. And the reason being is because, as you notice, the implication has been often rewritten as a disjunction, so it is serving that same role. What's the conclusion? Well, the conclusion is going to be Q. That Q has to be true. So what's going on? Well, what you have here is you have two options, P or Q. That's the disjunction, P disjunction with Q. However, negation P says P can't be true. So what has to be true? Well, Q has to be true. That's what's left. This is basically the process of elimination in a sense. So, to show that this is a valid argument, you can use a truth table, but I'm going to be using the previously established properties to do a calculation. So, let's take the conjunction of the two premises and see if that implies the conclusion and see if this is the tautology. So, as before, I'm going to take the implication, rewrite it as negation of the hypothesis, disjunction with conclusion, and you notice this is already looking like the previous two cases for the laws of detachment. I'm going to have a distribution, I'm going to use De Morgan's laws, you're going to have the law of excluded middle, you're going to have the law of non-contradiction. The calculation is very similar. So let's go to it. We have the distributive law, so we distribute the conjunction on disjunction, giving the following. By the law of non-contradiction, negation of P conjunction with P will be a false statement, but false is the identity element for disjunction, giving me the following. I now use De Morgan's laws to distribute the negation, which changes conjunction to disjunction. Now, here's a big difference from the previous one specifically. The previous one you had two litotes showing up, but here I only have one. So I apply Litotes' law to the double negation on P, which gives me just P. I now have disjunction on disjunction, associative law. I can regroup those so that the Q's are together. So negation of Q, disjunction with Q. So by the law of excluded middle, that will be a true statement, which will absorb the P, giving me my tautology. Indeed, this is a valid argument. And as stated before, this argument is a form of case-based reasoning. You have two cases, P or Q. You've eliminated one of them, leaving you with the other one. So indeed, you are eliminating options one at a time. And what you'd like to do is do this multiple times so that you can end up essentially eliminating cases one by one, giving you a case-based approach. Now let's look at some examples of doing elimination in this manner. So in this example, let's consider this first premise. The first premise is going to be cats are mammals or reptiles. So that is cats are mammals is the P. My Q is cats are reptiles. So P disjunction with Q. My second premise is going to be cats are not reptiles. So there's my negation of one of the two premises, in this case negation of Q. So I have P disjunction with Q and not Q. So by the elimination process that I just described, the modus tolendos ponens, that will tell me that P must be true. So therefore cats are mammals. So this is a elimination process. Here's a second example of something similar. So my first premise is, I will read a book or play a video game tonight. So my P in this case is, I will read a book. My Q is, I will play a video game tonight. So P disjunction with Q. My second premise is, I will not play a video game tonight. So this is my negation of Q. So I have P disjunction with Q and negation Q. So by process of elimination, what must be true? Well, it would be P, I will read a book. So therefore, I will read a book tonight. So this is another example of an elimination. And that's where we'll stop for today. Next time we'll discuss more advanced arguments and proofs. Below is a list of references for today's video. We have Gensler's Introduction to Logic, Magnus's For All X, Suppes and Hill's First Course in Mathematical Logic, and Suppes's Introduction to Logic. If you liked today's video, go ahead and hit the like button below. If you have a comment or question, go ahead and leave that below as well, and we'll respond to you as soon as we can. Thank you for your time, and we'll see you next time. See you then.